Have you ever looked up at the moon and wondered why it never seems to make a mistake? Night after night, year after year, century after century, it circles our planet with astonishing precision. Every civilization in history has watched the same silent companion drift across the sky. It has inspired myths, guided sailors across oceans, marked calendars, and even determined the rhythm of life itself. Yet behind this familiar sight hides one of the greatest ideas humanity has ever discovered. Because according to everything your intuition tells you, the moon should already be gone. Gravity is constantly pulling it toward Earth. Every single second, the moon is being dragged inward by our planet's gravity. If gravity always pulls objects down, why doesn't the moon simply fall? Even stranger in one sense, it actually is falling. The moon has been falling toward Earth continuously for more than 4 billion years, and yet it has never crashed. How can something fall forever without ever reaching the ground? The answer begins with an apple falling from a tree, stretches across the mathematics of Isaac Newton, bends through Albert Einstein's curved spacetime, reaches into the birth of our solar system, and eventually connects to the motion of galaxies themselves. Along the way, we'll discover that orbits are not magical paths painted across space. Gravity isn't quite the force most people imagine, and even our own planet is participating in a cosmic dance far larger than the moon's journey around Earth. By the end, you'll realize that every satellite, every planet, every star orbiting the Milky Way, and perhaps even entire galaxies orbiting each other, are all participating in the same profound idea. Once you truly understand why the moon never falls, you'll never look at the night sky the same way again. Imagine standing in a wide open field and throwing a baseball. No matter how hard you throw it, it eventually curves downward and lands on the ground. Throw it faster and it travels farther before hitting the earth. Throw it even faster and it stays in the air longer. Your everyday experience teaches you something very simple. Gravity always wins. It doesn't matter whether you're throwing a baseball, dropping a feather in a vacuum, launching an arrow, or jumping into the air. Eventually, everything comes back down. This seems so obvious that we rarely question it. Gravity pulls things downward. End of story. For thousands of years, this appeared to describe the entire universe. People watched apples fall from trees, stones tumble down hills, rain descend from clouds, and concluded that heavenly objects must obey completely different rules. The moon seemed fundamentally different from everything on Earth. After all, nothing anyone had ever seen remained suspended in the sky forever. Everything fell, except the moon. Night after night it returned. Month after month it repeated the same journey. Year after year, it never seemed to lose its path. It almost appeared as though the moon belonged to a different universe with different laws. Many ancient civilizations believed exactly that. Aristotle proposed that Earth and the heavens were governed by entirely separate sets of principles. According to this view, earthly objects naturally moved downward because they were imperfect, while celestial bodies moved in perfect circles because the heavens were divine and unchanging. For nearly 2,000 years, this explanation satisfied humanity. There seemed little reason to doubt it. After all, nobody had ever visited the moon. Nobody had launched a spacecraft. Nobody possessed telescopes powerful enough to reveal its mountains or craters. The moon was simply part of the heavens, separate, perfect, untouchable. But nature had been quietly hiding an extraordinary secret. The moon wasn't breaking the rules. It was obeying exactly the same laws as every falling stone on Earth. The difference wasn't the force. The difference was the motion. That realization would eventually transform not only astronomy but all of physics. Long before Newton was born, another scientist began noticing cracks in humanity's understanding of the universe. Galileo Galilei did something revolutionary. Instead of accepting ancient ideas simply because respected philosophers had taught them, he performed experiments. He rolled balls down inclined planes, he carefully measured motion, he timed falling objects, and most importantly, he began asking questions that seemed almost childishly simple. What happens if nothing stops an object from moving? This question sounds obvious today, but in Galileo's time, the accepted belief was that objects naturally wanted to come to rest. A moving cart eventually stopped. A rolling stone eventually stopped. Everything eventually stopped. It seemed perfectly reasonable. Galileo realized something astonishing. Objects weren't stopping because motion naturally ended. They were stopping because something else was interfering. Friction, air resistance, tiny forces constantly stealing energy away. Imagine sliding a hockey puck across perfectly smooth ice. It travels much farther than across rough concrete. Now imagine ice with absolutely no friction whatsoever. The puck would never stop. Not because something keeps pushing it, but because nothing is slowing it down. Motion, Galileo realized, is surprisingly stubborn. Objects don't require a force to keep moving. They require a force to change their motion. This single insight became one of the foundations upon which modern physics was built. It also contained the first clue to the moon's greatest mystery. Suppose you could somehow throw a baseball sideways so fast that while gravity pulled it downward, the Earth curved away beneath it at exactly the same rate. The ball would constantly fall, yet never reach the ground. At first, this sounds impossible. But remember something remarkable about Earth. It isn't flat. It curves away in every direction. Walk far enough, and you eventually return to where you started. That curvature changes everything. Imagine standing on an impossibly tall mountain, rising above the atmosphere, higher than airplanes, higher than weather, higher than any mountain on Earth. Now imagine possessing a cannon unlike anything humans have ever built. This cannon can launch cannonballs faster and faster. Fire one slowly. It follows a familiar curved path before crashing into the ground. Increase the speed. It lands much farther away. Increase it again, farther still. Now imagine increasing the speed to nearly 8 kilometers every second. Something extraordinary happens. As the cannonball falls toward Earth under gravity, Earth's surface curves downward beneath it at precisely the same rate. The cannonball never catches the ground. Instead, it keeps missing, forever. It has become an orbiting satellite. Nothing magical happened. Gravity never disappeared. The cannonball is still falling every second. It simply never reaches what it's falling toward. This thought experiment would later become one of the most famous illustrations in physics because it reveals something deeply counterintuitive. Orbiting isn't the opposite of falling. Orbiting is a very special kind of falling. The moon isn't escaping gravity. Gravity is doing exactly what it has always done. It is pulling continuously inward. Without gravity, the moon wouldn't remain near Earth at all. It would immediately fly off in a straight line into interplanetary space. Instead, gravity constantly bends its motion. Not enough to make it crash. Just enough to keep changing the direction in which it travels. Every second, the moon attempts to continue moving straight ahead. Every second, Earth's gravity redirects it slightly inward. The result is neither escape nor collision. It is an endless balance between forward motion and inward acceleration. That elegant balance is one of the most beautiful ideas ever discovered in science. And it doesn't apply only to the moon. It governs every artificial satellite, every planet, every comet, every binary star, even the immense journey of our solar system around the center of the Milky Way. The same principle that keeps the moon above your head tonight also guides stars separated by tens of thousands of light years as they circle the heart of our galaxy. The universe, despite its unimaginable scale, often repeats the same simple ideas in endlessly surprising ways. The realization that an orbit is simply an object falling forever sounds elegant, but it immediately raises another question. If the moon is constantly falling, then what exactly is pulling it? Today, almost everyone answers that question with a single word: gravity. Yet that answer hides another mystery. What is gravity? For thousands of years, people believed gravity was obvious because its effects were obvious. Things fall, rain falls, rocks fall. We stay firmly attached to the ground instead of drifting into space. But none of those observations explain what gravity actually is. They merely describe what gravity does. To understand why the moon remains in orbit, humanity first had to realize that gravity does not suddenly stop at the top of a mountain or at the edge of the atmosphere. It reaches astonishing distances. This idea seems natural today because we grew up seeing pictures of planets and satellites. But in the 17th century, it required an enormous leap of imagination. The tallest mountains rise only a few kilometers above sea level. Clouds float perhaps 10 or 15 kilometers high. The moon, however, is nearly 384,400 kilometers away. That is roughly 30 Earth diameters. If gravity truly reached that far, then Earth was influencing an object almost 400,000 kilometers away without any visible connection. No rope, no beam, no invisible chain anyone could detect. Just empty space. That sounded almost magical. Even Newton himself found the idea deeply unsettling. One of the greatest misunderstandings in popular history is the famous apple story. People often imagine Isaac Newton sitting beneath a tree, an apple falling onto his head, and instantly discovering gravity. History is almost certainly less dramatic. According to accounts recorded later in his life, Newton merely observed a falling apple and began asking an extraordinary question. Could the same force that pulls this apple downward also be reaching all the way to the moon? That question changed science forever. Notice how different this is from asking why apples fall. Everyone already knew apples fell. Newton's genius was recognizing that perhaps the heavens and the earth were not separate worlds after all. Perhaps the moon and the apple obeyed exactly the same law. It was a breathtakingly simple idea. If true, then the universe suddenly became understandable in a completely new way. The same mathematics describing a pebble dropping from your hand could also describe planets moving around the sun. One law, everywhere. Newton eventually expressed this idea mathematically in what became the law of universal gravitation. The word universal was the revolutionary part. Not earthly gravitation, not celestial gravitation, universal. Everything with mass attracts everything else. Every person in the world is pulling on every other person. Every tree pulls on every bird. Every mountain attracts every comet floating overhead. Even your own body exerts a tiny gravitational pull on the moon. The force is unimaginably small, but according to Newton's equations, it is real. Gravity is not something Earth possesses uniquely. It is woven into every piece of matter in the universe. The reason Earth's gravity dominates our everyday lives is simply because Earth contains an enormous amount of mass concentrated beneath our feet. Its pull overwhelms almost everything nearby. Newton discovered something else remarkable. Gravity weakens with distance. Not gradually, very rapidly. Double your distance from Earth, and gravity becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. This relationship is known as the inverse square law, and it appears repeatedly throughout physics. Light spreads this way. Electric fields behave this way. Many fundamental interactions reveal the same geometric pattern, because space itself has 3 dimensions. As influence spreads outward in every direction, it must cover larger and larger spherical surfaces. The same amount of influence becomes distributed over increasingly vast areas. The mathematics is beautiful because it emerges naturally from geometry rather than arbitrary rules. Yet, despite becoming weaker, gravity never truly disappears. Even here lies another fascinating fact. Earth's gravity where the International Space Station orbits is still about 90% as strong as it is on the ground. Many people imagine astronauts floating because there is almost no gravity. The opposite is true. They float because they are continuously falling around Earth at extraordinary speed. Exactly like the moon. Exactly like Newton's imaginary cannonball. Exactly like every satellite humanity has ever launched. The International Space Station circles Earth approximately every 90 minutes because it is moving sideways at nearly 7.7 kilometers every second. Gravity keeps pulling it downward. Its enormous forward speed keeps making it miss. Every orbit is another demonstration that Galileo and Newton were right. Motion continues, gravity redirects. Neither wins completely. Instead, nature finds a balance. But Newton still faced a question that even he could not answer. How does gravity travel through empty space? Imagine the moon suddenly disappearing. Would Earth's gravity instantly vanish from its location, or would that change take time to travel? Newton honestly admitted that he did not know. In a letter written in 1692, he expressed discomfort with the idea that one object could somehow influence another across empty space without any intermediary. He wrote that such action at a distance was, in his words, so great an absurdity that he believed no competent thinker could truly accept it without some deeper mechanism. Remarkably, Newton left the mystery unsolved. His equations predicted motion with astonishing accuracy, but they did not explain why gravity existed. Physics had learned how gravity behaves, it still had not learned what gravity is. That mystery would wait more than 2 centuries before another extraordinary mind approached it from an entirely different direction. Before we reach Einstein, however, we need to appreciate just how successful Newton's picture became. Using nothing more than mathematics, astronomers began predicting the future. They could calculate eclipses decades in advance. They could determine where planets would appear years later. Most astonishingly, they could discover objects nobody had ever seen. In the early 19th century, astronomers noticed something peculiar. The planet Uranus refused to follow exactly the path Newton's equations predicted. The discrepancy was tiny, barely noticeable, but it persisted. Rather than abandoning Newton's theory, 2 mathematicians working independently suggested a bold explanation. Perhaps another unseen planet was tugging gently on Uranus. If gravity reached across the solar system, then an invisible world's pull could slightly alter another planet's orbit. Using only Newton's mathematics, they calculated where this unknown planet should be. In 1846, astronomers pointed their telescopes toward the predicted location. There it was, Neptune. Humanity had discovered an entire planet using mathematics before actually seeing it. Few moments better illustrate the extraordinary power of physical laws. Nature had become predictable. The universe was speaking mathematics. Yet even this triumph hinted that the story was incomplete. As measurements became more precise, astronomers noticed another subtle anomaly. Mercury, the closest planet to the Sun, drifted through space in a way Newton's equations could not perfectly explain. Its orbit slowly rotated over time. The difference was tiny, only about 43 arcseconds per century, less than 1 degree in nearly 8,000 years. Most people would never notice such a minute deviation. Scientists did, because nature does not make mistakes. Whenever reality disagrees with theory, one of 2 things must happen. Either the measurements are wrong, or the theory is incomplete. For decades, astronomers searched for another hidden planet near the Sun that might explain Mercury's strange motion. They even gave this hypothetical world a name, Vulcan. No such planet was ever found. The mystery remained. No one realized that the solution required completely rethinking gravity itself. But before that revolution arrived, another mystery was quietly unfolding much closer to home. The moon's orbit is not perfectly circular. It slowly changes. Its distance from Earth varies by tens of thousands of kilometers. Its orbital plane gently shifts over long periods. Its orientation slowly rotates. Even more surprisingly, the moon is gradually moving away from Earth. Not by kilometers, not even by meters, Only about 3.8 centimeters every year, roughly the speed at which your fingernails grow. It sounds insignificant, yet over millions of years those centimeters accumulate into thousands of kilometers. How do scientists know something so unbelievably precise? The answer reflects one of humanity's greatest engineering achievements. During the Apollo missions, astronauts placed special mirrors called retroreflectors on the lunar surface. These mirrors have no power source, no electronics, no computers. Even today, decades later, observatories on Earth fire laser pulses toward the moon. A tiny fraction of those photons strike the mirrors and bounce directly back. By measuring the travel time of light, moving at nearly 300,000 kilometers every second, scientists can determine the Earth-Moon distance with astonishing precision, down to mere centimeters. Those measurements reveal something extraordinary. The Moon is escaping. Very slowly. Not because gravity is weakening, not because the Moon's engines are firing, but because Earth itself is giving the Moon energy. How can a planet transfer energy to its satellite without touching it? The answer lies in tides. Most people think tides are simply rising and falling oceans. In reality, tides are evidence that gravity is stretching an entire planet. Earth is not perfectly rigid. The Moon's gravity slightly deforms our oceans, our crust, and even our mantle. As Earth rotates faster than the Moon orbits, those tidal bulges become pulled slightly ahead of the Earth-Moon line. That tiny misalignment changes everything. Instead of pulling directly backward, Earth's tidal bulge pulls the Moon slightly forward along its orbit. That small forward tug increases the Moon's orbital energy. As strange as it sounds, adding energy to an orbit actually moves an object farther away. The Moon climbs into a larger orbit. Its orbital speed decreases slightly. Its distance increases. Earth pays the price. Every transfer of energy slows Earth's rotation just a little. Hundreds of millions of years ago, a day on Earth lasted roughly 22 hours. Go back even farther, over 1 billion years, and days were significantly shorter still. The Earth has been gradually losing rotational energy for immense spans of geological time. One day, far in the future, if the Sun's evolution did not intervene first, Earth and Moon would become tidally locked to each other. Each would always show the same face to the other. The Moon already reached this state long ago. It rotates exactly once during each orbit. That is why the same lunar hemisphere always faces Earth. The so-called far side of the Moon is not permanently dark. It receives sunlight just as often as the near side. It remained hidden from humanity simply because orbital mechanics had locked the Moon's rotation with exquisite precision. Nature had performed this synchronization automatically over billions of years. Nothing instructed the Moon to behave this way. Gravity patiently reshaped its rotation until the lowest energy configuration emerged naturally. The deeper scientists looked, the more they realized that gravity was doing far more than keeping the Moon in orbit. It was sculpting worlds, changing the length of Earth's day, heating planetary interiors, driving geological evolution, and beyond our solar system, gravity was orchestrating dances involving stars, black holes, entire star clusters, and galaxies containing hundreds of billions of suns. The same invisible interaction keeping tonight's Moon above your horizon would eventually lead us toward one of the astonishing discoveries ever made, that perhaps gravity is not a force in the ordinary sense at all. There is another way to look at the Moon's orbit that is even more unsettling. Imagine, just for a moment, that the Moon could think. From its own perspective, it is not trying to circle Earth. It is simply trying to move straight ahead. Every instant, the Moon wants to continue in exactly the direction it is already traveling. It has no desire to curve. It has no awareness that Earth even exists. According to one of the deepest principles in physics, an object in motion naturally continues moving in a straight line unless something changes that motion. That principle, which later became Newton's first law of motion, is so fundamental that nearly every branch of physics depends on it. Yet here lies the paradox. If the moon naturally wants to move in a straight line, why does its path curve continuously? Something must be changing its direction every second. Notice something subtle. Changing direction is just as important as changing speed. Imagine driving a car around a perfectly circular racetrack. Your speedometer always reads exactly 100 kilometers per hour. You never accelerate. Or do you? Most people would say no. Physics says yes. Acceleration is not merely speeding up. Acceleration means any change in velocity. Velocity includes both speed and direction. Even if your speed never changes, continuously turning the steering wheel changes your direction. That means you are accelerating every moment. The moon is doing exactly the same thing. Its speed remains nearly constant throughout most of its orbit, yet its direction is changing every second. That constant inward acceleration is produced by Earth's gravity. The moon is not constantly speeding up toward Earth. It is constantly changing direction toward Earth. This distinction is one of the most misunderstood ideas in orbital mechanics. Many people imagine gravity acting like an invisible rope pulling the moon inward. But if that were true, the moon would spiral directly into Earth. Instead, gravity behaves more like a gentle hand continuously nudging the moon sideways, just enough that its straight path becomes a graceful curve. Remove that tiny continuous change in direction, and the moon would not stop. It would not hover. It would disappear into interplanetary space almost instantly, moving forever along the straight path it happened to occupy at that exact moment. This idea becomes even stranger when viewed from Einstein's perspective. But before we reach him, we should appreciate something remarkable about Newton's universe. Newton believed space itself was perfectly empty, an enormous invisible stage. Planets moved across it. Stars moved across it. Galaxies, had Newton known they existed, would have moved across it too. Space itself never participated. It simply existed, absolute, unchanging. Time behaved the same way. Every clock in the universe, Newton imagined, ultimately measured the same universal time. Whether you stood on Earth or rode beside the moon, 1 second was always 1 second. The universe possessed a gigantic invisible clock ticking identically for everyone. For more than 2 centuries, this picture worked extraordinarily well. It predicted eclipses, planetary motion, comets, ocean tides. Spacecraft trajectories centuries later would still begin using Newton's equations because they remain astonishingly accurate under ordinary conditions. Yet tiny cracks were beginning to appear. One of the first came not from astronomy, but from light. In the 19th century, physicists discovered that light always travels at exactly the same speed in a vacuum, approximately 299,792 kilometers every second. At first, this seemed like another interesting measurement. Then people asked an innocent question. Compared to what? Imagine standing inside a train moving at 100 kilometers per hour. If you walk toward the front of the train at 5 kilometers per hour, someone standing beside the tracks measures your speed as roughly 105 kilometers per hour. This feels completely natural. Velocities simply add together. Everything in daily life behaves this way. Throw a baseball forward from a moving truck. Its speed relative to the ground becomes the truck's speed plus the ball's speed. Simple. Now imagine switching the baseball for a flashlight. According to Newton's universe, someone standing beside the tracks should measure the light beam as traveling faster than someone riding inside the train. But experiment after experiment refused to agree. No matter how fast the observer moved, the speed of light remained exactly the same. Nature was breaking everyone's expectations. At first, physicists suspected their instruments. then their calculations. Eventually, they realized something much more disturbing. Perhaps space and time themselves were not behaving the way Newton imagined. Into this growing mystery stepped a young patent clerk working in Switzerland, Albert Einstein. In 1905, Einstein proposed something almost absurd. Instead of changing the speed of light to match different observers, what if space and time itself changed instead? It sounded impossible. Yet every experiment supported it. Lengths could contract. Time could slow. Events that seemed simultaneous for one observer might occur at different times for another. Reality itself became flexible. The universe had no universal clock after all. Time depended upon motion. A decade later, Einstein asked another question. If motion changes time, what does gravity do? He later described the realization as the happiest thought of his life. Imagine standing inside a sealed elevator. If the elevator floats quietly in deep space, you feel weightless. Now imagine rockets begin accelerating the elevator upward. Suddenly, your feet press against the floor. A dropped ball falls. Water pours downward. Everything behaves exactly as though gravity had appeared. But has gravity actually appeared? No. The floor is simply accelerating upward into you. Einstein realized something astonishing. There is no local experiment capable of distinguishing between gravity and acceleration. This became known as the equivalence principle. It sounds technical. Its consequences transformed our understanding of the universe. Suppose you release the moon and allow it to fall freely. From its own perspective, it does not feel any force at all. Just as astronauts aboard the International Space Station float despite Earth's gravity remaining strong, the moon itself is in continuous free fall. In its own frame of reference, it is weightless. That statement sounds almost contradictory. How can something experiencing Earth's gravity not feel gravity? Because feeling weight and experiencing gravity are not exactly the same thing. When you stand on Earth's surface, gravity tries to pull you toward the center of the planet. But the ground refuses to let you fall. The pressure beneath your feet pushes upward. That upward push is what you experience as weight. Remove the ground, and gravity remains. Yet the sensation disappears. Astronauts do not float because gravity vanished. They float because nothing prevents them from following gravity. The moon exists in precisely that condition. It is endlessly falling. Nothing interrupts the fall. Then Einstein made one of the greatest conceptual leaps in history. Perhaps gravity is not a force pulling objects. Perhaps gravity is geometry. Imagine stretching a perfectly smooth rubber sheet. Place a heavy bowling ball in its center. The sheet bends. Now roll a marble nearby. The marble curves toward the bowling ball. Did the bowling ball pull the marble sideways? Not exactly. The marble simply followed the curved surface beneath it. The famous rubber sheet analogy is imperfect because it uses Earth's gravity to explain gravity itself, but it captures one essential idea. Mass changes the geometry around it. Earth reshapes spacetime. The moon follows the straightest possible path through that curved spacetime. To us, the path appears curved. To the moon, it is simply moving naturally. His idea overturned more than 200 years of scientific thinking. Earth is not reaching outward and pulling the moon. Earth changes the structure of space-time surrounding it. The moon responds to that geometry. John Archibald Wheeler later summarized Einstein's insight with one of the most famous descriptions in physics. Space-time tells matter how to move. Matter tells space-time how to curve. Few sentences better capture modern gravity. Suddenly, countless mysteries became understandable. Mercury's strange orbit? Solved. The bending of starlight passing near the sun? Predicted before it was observed. Time slowing near massive objects? Measured repeatedly using atomic clocks? Even GPS satellites orbiting Earth must constantly correct for both Einstein's special and general relativity. Without those corrections, navigation errors would accumulate by several kilometers every day. Every time your phone determines your location, it quietly confirms Einstein's theory. But Einstein's gravity revealed something even more astonishing about the Moon. The Earth-Moon system is not isolated. It exists inside the Sun's curved spacetime. The entire solar system moves around the Milky Way within an even larger gravitational landscape. The Milky Way itself falls through the gravitational field created by neighboring galaxies. Our local group drifts toward the Virgo cluster. The Virgo cluster moves within the Laniakea supercluster. Beyond that, immense concentrations of invisible dark matter shape the motions of entire galaxy populations over hundreds of millions of light-years. The Moon's quiet orbit around Earth is merely one tiny note in an unimaginably vast cosmic symphony. The same geometry that guides a satellite a few hundred kilometers above Earth also governs stars orbiting the supermassive black hole at the center of our galaxy, galaxies orbiting within clusters, and perhaps even the evolution of the universe itself. And yet, despite Einstein's astonishing success, one profound mystery remains. His equations describe how gravity shapes spacetime with exquisite precision, but they still do not tell us why spacetime exists, why mass curves it, or how gravity fits together with the strange quantum world governing atoms, the very atoms that make up the Moon, the Earth, and you. The deeper we understand the Moon's orbit, the more it becomes clear that this familiar companion in our night sky is quietly pointing toward one of the greatest unsolved problems in all of modern physics.
If the story ended with Einstein, physics would feel wonderfully complete. The Moon follows curved spacetime. Earth curves spacetime because it has mass. Problem solved. Except it wasn't. In fact, Einstein's greatest triumph also revealed one of the deepest cracks in our understanding of reality. To see why, we must zoom inward, far inward, until the Moon itself disappears, until Earth disappears, until even atoms begin to dissolve into something stranger. Everything you've seen around you, mountains, oceans, your own body, the Moon hanging above the horizon, is built from atoms. Each atom is almost entirely empty space. If you could enlarge an atom until its nucleus were the size of a marble, the electrons would orbit several football fields away. Between them, almost nothing. This is one of the most astonishing facts in science. The Moon looks like a solid world. Earth feels solid beneath your feet, yet both are constructed almost entirely from emptiness. That emptiness raises an uncomfortable question. If atoms are mostly empty space, why doesn't the Moon slowly collapse into itself? Why doesn't Earth? Why don't you? The answer involves forces much stronger than gravity. Gravity dominates the universe only because it never switches off. It is always attractive. It reaches infinitely far. But on atomic scales, gravity is astonishingly weak. Take two electrons. Their electrical repulsion is roughly 10 to the 42nd stronger than their gravitational attraction. That number is almost impossible to comprehend. It is a 1 followed by 42 zeros. If gravity were suddenly removed from an atom, almost nothing would change. If electromagnetism disappeared, atoms themselves would cease to exist. This teaches us something profound. The Moon survives because different forces dominate at different scales. Its atoms are held together primarily by electromagnetism and quantum mechanics. Its enormous collection of atoms forms a massive object. Only then does gravity become the dominant architect. Physics is layered. Different rules become important at different sizes.
Understanding the moon, therefore, requires understanding something much larger and much smaller. Gravity organizes worlds. Quantum mechanics organizes matter. Somehow, these two descriptions coexist, yet no one has ever successfully united them into one complete theory. This is where the moon becomes unexpectedly important, because although its orbit seems enormous by human standards, Einstein treats the moon exactly as if it were a single object, a point. Its internal atoms don't matter. Its mountains don't matter. Its craters hardly matter. Even its composition hardly matters. Only its total mass. Nature is simplifying an incredibly complicated object. Imagine replacing the moon with a perfectly smooth sphere made entirely of iron, or ice, or diamond. Provided the total mass remained identical and the mass were distributed symmetrically, Earth's orbit calculations would barely notice the difference. Gravity appears astonishingly indifferent to composition. Gold falls exactly like aluminum. Hydrogen falls exactly like uranium. This puzzled Einstein enormously.
Why should gravity ignore what things are made of? No other force behaves this way. Electromagnetism cares about electric charge, the strong nuclear force cares about quarks, the weak interaction distinguishes among elementary particles. Gravity alone appears wonderfully democratic. Everything falls together. Galileo supposedly demonstrated this by dropping objects from the Leaning Tower of Pisa. Whether that famous experiment occurred exactly as legend describes remains uncertain. What matters is that centuries of increasingly precise experiments have confirmed the same principle. In 1971, during Apollo 15, astronaut David Scott stood on the moon holding a geological hammer in one hand and a feather in the other. There was essentially no atmosphere, no air resistance. He released both simultaneously. They struck the lunar surface together. Millions watched. Galileo's insight echoed across 4 centuries. Gravity does not care whether something is heavy or light. It responds only to mass energy itself. That simple observation later became one of Einstein's starting points. Yet another mystery quietly emerges. The moon's orbit appears almost effortless. No fuel, no engines, no corrections. For over 4 billion years, it has remained remarkably stable. How? Because nature is extraordinarily conservative. Physicists use a word that appears repeatedly across nearly every successful theory: conservation. Certain quantities never disappear. They may transform, they may move, they may exchange between objects, but the total remains constant. Energy, momentum, angular momentum, electric charge. These conservation laws are among the deepest principles ever discovered. They are so reliable that when physicists observe something apparently violating them, they usually assume something unseen must exist. Entire particles have been predicted this way. Neutrinos were proposed because energy seemed to vanish during radioactive decay. It wasn't disappearing, something invisible was carrying it away. The moon's orbit is another magnificent demonstration of conservation. As Earth pulls inward, the moon continuously converts gravitational potential energy into motion. As it moves farther away in its orbit, some motion transforms back into potential energy. Nothing is lost. Everything changes form. Nature keeps immaculate accounts. This becomes easier to appreciate if you imagine a giant cosmic pendulum. A pendulum constantly exchanges energy. At the highest point, it possesses maximum gravitational potential energy. At the lowest point, maximum kinetic energy. The total remains nearly constant. The moon performs a similar exchange while traveling through its slightly elliptical orbit. Near perigee, when closest to Earth, it moves faster. Near apogee, farther away, it moves slower. Johannes Kepler never knew about gravity. He simply examined decades of remarkably precise observations made by the Danish astronomer Tycho Brahe. Brahe had devoted much of his life measuring planetary positions with extraordinary care, decades before the invention of the telescope.
His observations were the finest astronomical data humanity possessed. When Brahe died, Kepler inherited that priceless treasure. For years, Kepler struggled to force Mars into perfect circles because everyone believed heavenly motion had to be circular. Again and again, reality refused. The error was tiny, only a few arc minutes. Many astronomers would have ignored it. Kepler did not. He later wrote that if he had believed it acceptable to ignore those 8 minutes of arc, he could have repaired his entire theory. Instead, those tiny discrepancies forced him to abandon centuries of accepted belief. Nature cared more about truth than elegance. The orbit was not a circle. It was an ellipse. That realization transformed astronomy forever. Today, we often celebrate Newton because he explained gravity. But Newton himself openly acknowledged standing upon Kepler's work. Without Kepler's relentless commitment to observational accuracy, Newton might never have discovered universal gravitation. Science advances because observations discipline imagination. The moon's orbit is not perfect because nature rarely prefers perfection. Ellipses arise naturally. Perfect circles require special conditions. Reality chooses what mathematics permits most easily. Even today, no orbit remains perfectly unchanged. Every planet exerts tiny gravitational tugs on every other. Jupiter gently influences Earth. Venus slightly perturbs Mercury. Saturn affects Jupiter. The Sun itself wobbles because all its planets pull back upon it. Even the Moon is not orbiting a perfectly stationary Earth. Both Earth and Moon actually orbit a common point, called the barycenter. This surprises many people. We often imagine the Moon circling Earth while Earth remains fixed. Reality is subtler. Because the Moon contains about 1/80th of Earth's mass, Earth also moves. The barycenter lies roughly 4,700 kilometers from Earth's center, still inside our planet, but not at its exact center. As the Moon completes one orbit, Earth performs a tiny monthly wobble around this invisible point. Neither object truly stands still. Both dance together. This simple idea scales upward beautifully. The Sun does not remain motionless while planets orbit it. It also wobbles around the solar system's barycenter, largely because of Jupiter's enormous mass. Astronomers use precisely these stellar wobbles to discover planets orbiting distant stars. Sometimes they never see the planet directly. They detect only the tiny rhythmic motion of its parent star. A distant sun rocks gently back and forth. Something unseen must be pulling it. Again, gravity reveals invisible worlds. The same principle that allowed mathematicians to predict Neptune now allows astronomers to discover planets hundreds or even thousands of light years away. Some of those worlds may possess moons of their own. Some may have oceans. Some may experience eclipses beneath alien skies. And around each of them, gravity performs exactly the same quiet choreography that has unfolded above Earth for billions of years. The deeper we look, the harder it becomes to escape one astonishing conclusion. The Moon is not merely orbiting Earth. It is participating in one of the universe's oldest patterns, a pattern repeated from artificial satellites to binary stars, from planets around distant suns to galaxies orbiting inside vast clusters. The equations barely change, only the scale does. And as we continue expanding outward, we begin to discover something even stranger. The same gravity that keeps the Moon from falling to Earth appears unable to explain the motion of galaxies themselves. Somewhere beyond the orbit of the Moon, beyond the solar system, beyond the Milky Way, gravity begins behaving as though an invisible universe is hiding in plain sight. References: Isaac Newton, Philosophiae Naturalis Principia Mathematica, 1687. Johannes Kepler, Astronomia Nova, 1609. Albert Einstein, The Foundation of the General Relativity, 1916. There is one final perspective that almost no one considers when looking at the Moon. Throughout this journey, we've quietly assumed that the Moon is orbiting Earth. But from the viewpoint of the universe, that statement is incomplete. Neither the Earth nor the Moon is standing still. At this very moment, while the Moon circles our planet every 27.3 days, Earth is racing around the Sun at nearly 30 kilometers every second. During one lunar orbit, Earth travels more than 70 million kilometers around the Sun. The Moon comes along for the ride. Its path through the solar system is not a simple circle. It is a graceful wave wrapped around Earth's orbit. If you could freeze the solar system and watch from far above, the Moon would appear to weave gently around Earth's path without ever doubling back toward the Sun. Even when the Moon is on the far side of Earth, it is still moving around the Sun at tremendous speed. In fact, the Moon is always falling toward the Sun as well. The Sun's gravitational pull on the Moon is actually more than twice as strong as Earth's gravitational pull. At first glance, that sounds impossible. If the Sun pulls harder, why doesn't it steal the Moon away? The answer reveals something subtle about gravity. Earth and Moon are both falling toward the Sun together. Imagine dropping two stones side by side. Neither falls towards the other. Both fall together. The Sun accelerates Earth and Moon almost equally because they are relatively close to one another compared with their distance from the Sun. What matters is not merely the strength of gravity, but the tiny difference in gravity across the Earth-Moon system. That difference is what allows the Moon to remain gravitationally bound to Earth while both continue orbiting the Sun. Nature builds hierarchies of motion. The Moon orbits Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way drifts within the local group. The local group moves within the Virgo cluster. The Virgo cluster flows within the immense structure known as Laniakea. Every level is another orbit nested inside an even larger one. No object in the universe enjoys absolute rest. Motion exists within motion, orbit within orbit, falling within falling. The Moon is not simply falling toward Earth. It is participating in a cascade of gravitational relationships extending hundreds of millions of light years. And yet, astonishingly, all of these motions emerge from the same mathematical principles Newton first recognized and Einstein later transformed. This remarkable unity is one of the greatest achievements of science. But the story does not end there, because when astronomers began measuring the motions of entire galaxies during the 20th century, something impossible appeared. Stars far from galactic centers were moving too quickly. According to everything Newton and Einstein predicted using only visible matter, many galaxies should gradually fly apart. Instead, they remained intact. Something unseen was providing additional gravity. Today, we call this mysterious ingredient dark matter. The name sounds pragmatic. In reality, it simply means we do not know what it is. It neither emits nor reflects detectable light. It has never been directly observed, yet its gravitational influence appears everywhere. Galaxy clusters bend light far more strongly than visible matter alone can explain. Galaxies rotate too rapidly. The large-scale structure of the universe itself seems impossible without additional unseen mass. Roughly 85% of all matter appears to be invisible. Think about what that means. Every mountain, every ocean, every planet, every star you've ever seen, every galaxy captured by the James Webb Telescope. Together, they account for only a small fraction of the universe's matter. The rest remains hidden. The Moon circles Earth because of gravity. Galaxies may survive because of something we still cannot identify. Our understanding has advanced enormously since Newton, yet some of the biggest questions remain unanswered. And perhaps the greatest mystery lies even deeper. General relativity describes gravity with extraordinary precision on enormous scales. Quantum mechanics describes atoms with astonishing accuracy on microscopic scales. Both theories have passed every experimental test within their domains, yet they refuse to merge into one complete description of reality. Inside black holes, during the first tiny fraction of a second after the Big Bang, perhaps even within space-time itself. Our best theories become mathematically incompatible. Somewhere, a deeper framework must exist. Physicists have proposed many possibilities. String theory imagines that the fundamental ingredients of reality are unimaginably tiny vibrating strings rather than point-like particles. Loop quantum gravity suggests that spacetime itself may possess an atomic structure woven from discrete quantum units. Other approaches attempt to describe gravity as an emergent phenomenon rather than a truly fundamental interaction. Some researchers even wonder whether spacetime itself emerges from quantum information. These ideas remain active areas of research. None has yet received definitive experimental confirmation. And that is precisely what makes modern physics so exciting. The moon, hanging peacefully above us, seems to represent certainty, yet it quietly points toward uncertainty. Every successful explanation reveals another deeper question. Newton explained why the moon remains in orbit. Einstein explained why Newton's picture works so well, while revealing an even richer geometry beneath it. Modern cosmology extended gravity across galaxies and the expanding universe. Quantum physics transformed our understanding of matter itself. Still, we do not know what gravity fundamentally is. We do not know why spacetime exists. We do not know what dark matter is made of. We do not know whether gravity must eventually be quantized. We do not know whether our universe is only one region of a much larger cosmic reality. The moon has become something unexpected, not merely a companion, not merely Earth's satellite, but a guide. For thousands of years it inspired myths. For centuries it inspired mathematics. Today it inspires questions at the frontiers of physics. Every night it reminds us that the universe is understandable, but never completely understood. Perhaps that is the most beautiful lesson science has ever taught. Knowledge does not erase mystery, it refines it. The questions become deeper, the answers become more elegant. The horizon simply moves farther away. So the next time you step outside after sunset and notice the moon quietly crossing the sky, remember what is truly happening. It is not hanging motionless above Earth. It is falling. It has been falling for more than 4 billion years. It falls without crashing because motion and gravity remain in perfect balance. It falls while carrying the history of our solar system.